In one of the earliest videos, we had come across the idea of fundamental theorem of algebra. I think it's important to look at that here again. It talks about, it says something about the number of roots a polynomial equation should have. So let's quickly delve into that and see how it goes. So fundamental theorem of algebra, otherwise known as FTA. So by the end of this lesson, you should be able to state the fundamental theorem of algebra clearly, explain what it means for a polynomial to have complex roots, then understand the idea that a degree n polynomial has exactly n complex roots counted with multiplicity. Then use the fundamental theorem of algebra to write polynomials as products of linear factors over C. Then distinguish between factorization over R and over C. So R is real and C is complex, I believe. Apply these ideas in worked examples. So let's see how this works. So recall we've talked about polynomials and roots, right? So a polynomial in one variable x with complex coefficients has the form p of x equals a n x raised by n plus a n minus 1 x raised by n minus 1 plus all of that plus a1 x plus a naught, where a naught, a1 up to a n are complex and a n is not equal to 0. I mean, when we say complex here, you should understand that all real numbers are also complex because real numbers are subset of complex, especially that, what makes a complex number complex is the root of minus 1. I mean, it's the root, yeah, it's the root of minus 1. So if you have 3 plus I, that's a complex number. If you have just 3, that's a real number. But you can write that, you can write 3 as 3 plus 0I. The only thing is that the imaginary part is 0. Okay, so we see all real numbers as complex too, because real numbers are subsets of complex numbers. So you should see it in that sense so you can understand what is really going on here. So if we say that a polynomial in one variable x with complex coefficients has this form, and the degree of p is n, so the highest power of x with non-zero coefficient, we've talked about that. A root of 0 of p is a complex number z such that p of z is equal to 0. Okay, I mean, before now we've called this C, we've called it R, and whatever you want to call it. But here we are looking at the fundamental theorem of algebra. So we are looking at the concept of complex numbers in a broad sense, considering that real numbers are subsets of complex numbers. So a very good example would be this. Let P of x be x squared minus 5x plus 6. In fact, I believe this is one of the most common expressions we have seen in this playlist so far. So we solve x squared minus 5x plus 6 equals 0 to find the roots, which is simply x minus 2 into x minus 3 when we factorize. So the roots are x equals 1, x equals 3. So they are real numbers, but remember, these are real numbers, but remember that real numbers are a subset of complex numbers, just like I said the other time. So this is 2, it is real, but it is a subset of complex number because you can say it is 2 plus 0i or 3 plus 0i, So every real root is automatically also a complex root. And that is, so this understanding is important for the statement of the fundamental theorem of algebra that you are going to. That's why I've been emphasizing the idea that you should understand that real numbers are subsets of complex numbers. So fundamental theorem of algebra, the basic statement tells us, fundamental theorem of algebra, basic form. Every non-constant polynomial with complex coefficients has at least one complex root, right? So at least one complex root. So if you have a linear polynomial, it has at least one complex root. Well, you might tell me that, okay, for 3x plus 5 equals 0, the answer is x equals minus 5 over 3. That is a complex root. Technically, it is real, but real is subset of complex. So that's the idea we're talking about here. So when we say complex root, now we are accommodating both real and complex. So we accommodate everything. So key phrase is here is non-constant. So non-constant polynomial, meaning that means that the degree n should be greater than or equal to 1. Very important. So so the polynomial should be at least one, of at least a linear one, or it can be more than that. It can be quadratic, cubic, quartic, quintic, and so on. At least one complex root, you see that here, means there exists some z belonging to C such that P of z is equal to 0. Sure. The meaning in informal sense, no matter how complicated a polynomial you build, as long as it is not constant, if you allow complex numbers, you are guaranteed to find at least one solution to P of x equals 0, no matter what you have. You can compare with the real case. Over R, some polynomials have no real roots. So, for instance, if you have Q of x equals x squared plus 1, it has no real solution, but it does have complex solutions. And the complex solutions, like we learned in the previous video, these complex solutions always come in pairs, right? Then we have a stronger form of this statement. We have stated the basic form of that statement that as far as you have a polynomial with non-zero coefficients, they are bound to have at least one complex root. But in a stricter sense, we have the next statement we're going to have now. So the stronger form, we talk about exactly n complex root with multiplicity. So a more precise and powerful version of the fundamental theorem of algebra is this, that if p of x is a polynomial of degree n greater than or equal to 1 with complex coefficients, then p of x has exactly n complex roots counted with multiplicity. So even if the root occurs more than once, okay, if you count the multiplicity, if you count the complex and everything, you have exactly n complex roots which correspond with the degree of the polynomial. So the multiplicity idea, of course, we've talked about. In fact, I made a special video on it, and I've mentioned it in several other videos. So if x minus r raised power k is a factor of p of x, but x minus r raised power k plus 1 is not, then r is called a root of multiplicity k, right? So if k is 1, r is a simple root. But if k is greater than 1, that is if you have, we've talked about this. If you have x minus 2 raised power 3, that means you have x is equal to 2 3 times. So if k is 1, you have a simple root. If k is greater than 1, you have a multiple root. So you have something of multiplicity greater than 1. So example, counting multiplicity. So let p of x be x minus 1 raised power 3x plus 2 squared. So the root of this expression will be, of this equation, of this polynomial, right, is x equals 1 with multiplicity 3 and x equal to with multiplicity 2 because of the powers on top of them. So total number of roots will be, with multiplicity, will be 3 plus 2, which is 5. So if you count 1 3 times and we count minus 2 2 times, the total root should be 5 because the overall degree of this polynomial is 5, adding 3 and 2 together, right? So, and indeed, the degree p of the polynomial is 3 plus 2, which is 5. So in general, if the distinct roots of p of x are r1, r2 up to rk with multiplicities m1, m2 up to mk, then m1 plus m2 plus all of that plus mk will be n, which matches the degree of the polynomial. And that is basically the statement of the complex of the fundamental theorem of algebra. The basic form is that if you have a polynomial that has a non-constant coefficient, you have at least one root. But the strong form is that if you have a polynomial of degree n, you have exactly n complex roots. N complex roots. That's if you count multiplicities. Okay, so what is the consequence? What are the consequences of this of factorization over C? So because of the fundamental theorem of algebra, we get a very important factorization result. Any non-constant polynomial with complex coefficients can be written as a product of linear factors over C. Exactly. So I think we saw this under a video where I talked about is it conjugate pairs or something like that? Complex roots and conjugate pairs. We tried something close to this there. So formally, if p of x has degree n, then there exist complex numbers a not 0 and roots r1, r2 up to rn listed with multiplicity such that p of x is equal to a into x minus r1, x minus r2 up to x minus rn. So the key points: complete linear factorization over C. So over C, now every polynomial splits into only linear factors x minus r, right? Then uniqueness up to order. So the roots r1 up to rn with multiplicities are uniquely determined by p up to the ordering of factors. So relation to factorization over r. So over r, some polynomials cannot be fully factored into linear factors with real coefficients. So that's why sometimes when we solve some polynomials, we discover that there are no real roots, but but you always find complex roots. As far as the fundamental theorem of algebra are concerned, even if you cannot find any real roots, there are definitely complex roots that align with the number of the degree of the polynomial. So over R, some polynomials cannot be fully factored into linear factors with real coefficients. Instead, they may have irreducible quadratic factors. So over C, those same quadratic factors split into linear factors with complex, possibly non-real roots, okay? Over R, for instance, x squared plus 1 is irreducible. It has no real roots. So over C, it factors as x squared plus 1, which is x minus I plus x plus I, because x squared plus 1 in the first place. What we are saying here, I think it's better I demonstrate it. So you have x squared plus 1 equals 0. So that means x squared is equal to minus 1. So x is equal to plus or minus square root of minus 1 if you take the square root of both sides. So that means that x is equal to root minus 1, right? Root minus 1 is I. So plus or minus I now. So these are two roots, right? So it means we are saying that x is equal to I or x is equal to minus I. Okay? So if this is true, it means that x minus I is equal to 0, or x plus I is equal to 0, like that. So if that is the case now, we know that following I think the zero property law. So if a quadratic is equal to 0, if you factor that quadratic, that if a polynomial expression is equal to 0, right? The product of the factors of the polynomial is equal to 0. That means that each of the factors, at least one of the factors will be 0. So in that case, now we have x minus I into x plus I is equal to 0. Now, how do you know that this is true? Right? So this is exactly the same thing as x squared minus 1, x squared plus 1 that brought us here. So how do we know this is true? Just try to expand it again. So you have x minus I into x plus I. That is x times x squared, x times plus x times plus I, that's xi, then minus I times x, that's minus xi, and lastly, minus I times I, that's I squared. Okay, so plus xi minus xi will cancel out. So you have x squared minus I squared. And don't forget, I squared, I squared is the same thing as square root of minus 1 all squared. Okay, so that means you have x squared minus 2 cancels root. So you have minus into minus 1 like that. Okay, that means you have x squared plus 1. So you can see that x minus I into x plus I is the same thing as x squared plus 1. So though there are no real roots, but even the complex root that exists, you can actually still write that expression as their product. So over R, this is irreducible, no real roots. But over C, it factors as x squared plus I equals x minus I into x plus I, where I squared is equal to minus 1. So let's talk about an example of that now. So degree and number of complex roots. So consider the polynomial p of x equals x cubed minus 1. So we can factor over R. We have x cubed minus 1 equals x minus 1 into x squared plus x plus 1. So the quadratic x squared plus x plus 1 has discriminant, using the discriminant now, a is 1, b is 1, c is 1. So that's b squared minus 4ac. That means we have 1 minus 4, which is minus 3 and less than 0. So it has no real roots, but it has complex roots. So this one has a real root. X is equal to 1, we know. So this one does not have real roots, but it has complex roots. So to find the complex root of x squared plus x plus 1 equals 0, we use the quadratic formula. That's x is minus 1 plus or minus root minus 3 over 2. So we have minus 1 plus or minus square root of minus 1 is I. Then we have root 3 over 2. So the three complex roots of p of x are x equals 1 from here. And from here now we have, these ones are always in conjugate pairs. We have minus 1 plus 1 over 1 root 3 over 2 and minus 1 root 3 over 2. So each root has multiplicity 1. So the total number of roots counted with the multiplicity is 3, which matches the degree. This is a polynomial of degree 3. And we have 1 real root and 2 complex roots. And the sweet thing about complex roots is that once you know one, just change. So there's automatically going to be another one when you change the sign in the middle. Like once you get this first one, this plus, you're automatically going to have the one with the minus. If you get the one with the plus, you're automatically going to have the one with the minus. If you have the one with the minus, you're automatically going to get the one with the plus. So over C now we see that x cubed minus 1 is equal to x minus 1 into x minus 1 plus 1 root 3 over 2 into x minus 1 minus 1 root 3 over 2. So you can factor any polynomial, even if it has no real roots, it definitely has complex roots. And that is why the fundamental theorem of algebra is important. So look at this now. Talking about multiple roots and multiplicity. Let p of x be x raised to the power 4 minus 2x cubed plus x squared. So if you factor step by step, you have p of x equals x squared is common to everything. So you have x squared into 2x squared into x squared minus 2x plus 1. So you can note that this x squared minus 2x plus 1 is the same thing as x minus 1 squared. So it means p of x is x squared into x minus 1 all squared. So identify the roots and their multiplicities. First of all, x squared is equal to 0 with multiplicity 2 because the power is 2. X minus 1 is equal to 0. That means x equals 1 with multiplicity 2. So this is a polynomial of degree 4. We already know. So if you add the multiplicities together, you have 4. So if you count multiplicities, total multiplicity is 2 plus 2, which is 4, which equals the degree of p, since degree p is 4. So this example illustrates the example n complex roots with multiplicity part of the fundamental theorem of algebra. So if you look at example 3 now, so complex factorization of a real polynomial. So factor the polynomial p of x equals x squared plus 1. So over C. So over complex now. So even if you don't get real roots. So first, factor over R using a difference of squares trick. So for instance, you have x squared plus 1, which is the same thing as x raised to the power 4 plus 2x squared plus 1 minus 2x squared. So this is us bringing in that. So it's like you're adding 2x squared to both sides, because we know if you have x raised to power 4, if you want to have difference of 2 squared, it's more like uh so you can bring this in. It's like you're introducing 0 so that x squared plus 2x squared plus 1 can simply be x squared plus 1 all squared. And then this 2x squared part can be root 2x all squared. So that's like a trick we are introducing into that. So we can get a perfect square out of this. Because x squared plus 1 squared is x raised to power 4 plus 2x squared. That's why we brought this in, plus the one we already had there. And this can be a square, this can be another square. So that we have x raised to power 4 plus 1. That's x squared plus 1 minus root 2x into x squared plus 1 plus root 2x. That is, x raised to power 4 now is the same thing as x squared minus root 2x plus 1 into x squared plus root 2x plus 1. So over R, this is a factorization into two quadratics. So we've been able to do this over R, right? Then we can factor again. We can then factor each quadratic over the complex number, over the complex system. So for x squared, this one, x squared minus root 2x plus 1 equals 0. We have the determinant, that's b squared, that's minus root 2 squared minus 4 times 1 times c. We have 2 minus 4, that's minus 2. That's definitely complex. So thus we have minus b. So b is minus root 2. So minus root 2, that's root 2, plus or minus b squared minus 4 is, which we already got to be minus 2 all over 2. So we have root 2 plus or minus I root 2 over 2. That is that is root 2 over 2 plus or minus I root 2 over 2. So we have that. Then for x squared plus root 2x plus 1 equals 0, we have the determinant again is another minus root 2. And then again, we have plus here. This is now minus root 2 over 2 plus or minus I root 2 over 2. Then we can factor all of that like we have. So we're expecting 4 results, right? So we now have, therefore, over C, x raised to power 4 plus 1 factors completely into linear factors. So it looks complicated, but it's straight to the point, right? X squared plus 4 is x minus the first one, you have root 2 over 2 plus I root 2 over 2. Then second one, x into root 2 over 2 minus I root 2 over 2 from here. Then the other two come from this one, x minus root 2 over 2 plus I root 2 over 2 into x minus root 2 minus root 2 over 2 minus I root 2 over 2. So we have 4 complex roots, each simple, matching degree P of 4. It is simple because we have these 4, each of the 4 roots has a multiplicity of 1. So they all add up to degree 4. That's the deal there. So we can then talk about real coefficients and conjugate pairs. So an important consequence when polynomial coefficients are real. So if a polynomial has real coefficients, then its non-real complex roots occur in conjugate pairs. That is established. So you can see once you have something containing I, there must automatically be one with a minus. Once you have minus root 2 over 2 plus I root 2 over 2, then there must be minus root 2 over 2 minus I root 2 over 2. Very important idea. So if you are told that a polynomial has maybe one of the roots of a polynomial is 2 minus I, you should automatically know that it also has another root, 2 plus I, automatic. So you can settle that first, and then you can now begin to look for the other roots based on that fact alone. So an important consequence when polynomial coefficients are real. So if polynomial has real coefficient, then its non-real complex roots occur in conjugate pairs. That's what I've established. So the meaning that suppose P of X has real coefficients and P of Z is 0, but some non-real complex number Z equals A plus BI with B not 0, that is the complex part is actually there. Then its complex conjugate would be Z bar, which is A minus BI. So if you have A plus BI, then there's A minus BI. If there's A plus minus BI, there's A plus BI. Which is also a root, such that P of Z bar is also 0. I mean, we established that when we talked about complex solutions, complex roots and conjugate pairs, I think. So the example is for P of X equals X squared plus 1, the roots are X equals 1, X equals I, and X equals minus I, which is I bar now. So this explains why over R, we often see irreducible quadratic factors corresponding to such conjugate pairs. For example, X squared plus 1. So you have plus I minus I like that. So in summary, what we are saying is that the fundamental theorem of algebra, for summary for fundamental theorem of algebra, roots and factorization. So for FTA in the basic form, every non-constant polynomial with complex coefficient has at least one complex root. That's the basic form. The stronger version, a degree n polynomial has exactly n complex roots counted with multiplicity. Very important. Now you have factorization over C. Any polynomial of degree n can be written as P of x equals a into x minus ri into x minus r2 up to x minus rn, where a is not zero and r1 up to rn belonging to C with multiplicity. So comparison to factorization over R. Over R, some polynomials remains with irreducible quadratic factors. That is, they have no real roots. But over C, every such quadratic factor splits further into linear factors, no matter what happens. So real coefficients and conjugate pairs now. If all coefficients are real, any non-real root z appears with its conjugate z bar as another root. So these facts give a complete picture of how polynomials behave over the complex numbers and explain why C is such a natural setting for studying polynomial equations. So in short, every polynomial equation has solutions. Even if they are not real, you have the complex ones which exist in conjugate pairs by you just changing the signs. So with that said, we have these 10 questions to deal with. So find all complex roots of the polynomial x cubed plus 8 and express P of x as the product of linear factor over C. This one is easily factorizable into, for x cubed plus 8, now that should be like x minus 2, because this is x cubed plus 2 cubed. I think that should be like x plus 2 into x minus 4x squared or something like that plus x squared, and then you have that complex part. Determine all the multiplicities of roots of the polynomial this and state its degree. So here we have 4 3 times, and you have minus I twice, basically. So factor the polynomial this completely over C. Okay, we can should I try this? I don't know. I'm tempted to do it, but let's see. I may come back to it. A polynomial of degree 5 has roots 2, minus 1, and 3 plus I. So you see these are 3 roots now. 1, 2, 3. So find the remaining roots if the coefficients are real and write the polynomial in factored form up to a non-zero constant. So you see, a polynomial of degree 5 has roots 2, minus 1, and 3 plus 1. It automatically has another root, which is 3 minus 1. I mean, since you have 3 plus 1, and then there's another 3 plus 1. So you can then multiply all this together, and then you can try to now get the fifth root based on that, right? So find the remaining roots if the coefficients are real and write the polynomial in factored form up to a non-zero constant. So show that polynomial this has no real roots, then factor it completely over C. Then the polynomial this x raised by 6 minus 1 has degree 6. Find all complex roots using known identities and verify that they satisfy the FTA. So here you can do the factoring method, like, okay, we can even start with difference of two squares. Okay, I think I'm tempted to take this on. This should be easier to handle than even the one I was going to do before. But it looks complicated, by the way, but it looks like combining uh difference of two squares and things like that. We should be able to handle this. Okay, x raised by 6 minus 1. So suppose a degree n polynomial has only two distinct roots. A multiplicity 3 and B multiplicity n minus 3. Write the polynomial in full factored form up to a constant. So factor this x raised by 4 plus 4 completely over C. So we can use the ideas we've seen before. So I'm just going to settle for x raised by 6 minus 1, and you can try the others. So let's go for this now. So we want to factor P of x equals x raised by 6 minus 1 completely, right? So first of all, we know this is okay. I mean, we can already get some real factors. So let's try to exhaust all the possibility of getting real factors. So first of all, it is clear that at okay, um so for R now, over the real number system now, it is clear that when x is 1 or minus 1, we get 0, right? So at x equals 1, we have P of 1 to be 1 raised by 6 minus 1, which is 1 minus 1, and that is 0. So x minus 1 is a factor, of x raised by 6 minus 1. That is settled. Another thing that is settled is x plus 1. So at x equals minus 1 now, again, we have P of minus 1 to be equal to, P of minus 1 is now minus 1 raised to power 6 minus 1. That is 1 minus 1 again, and that is again 0, okay? So again, x plus 1 is a factor. X plus 1 is a factor of x raised to power 6 minus 1. So now we have, with this, now we have taken care of two of the possible roots, okay? So we can write we can write we can write we can write that x raised to power 6 minus 1 is equal to x minus 1 into x plus 1 plus some expression q of x that we don't know. Okay, we can write this, and we know that this is x raised to power 6 minus 1 equals, so for this now we have, if you expand this now, this is x squared minus 1. Okay, x squared minus 1 into, multiplied by q of x, multiplied by q of x. So with this now, we already have two roots. So the four other roots we are looking for should be here. And from the look of things, they might just be complex. Because if we do have, okay, nothing else goes, minus 1 and plus 1 are settled. So for the other roots now, we may have to use long division, to get q of x now. Okay, to get q of x, we need to have like, we have q of x to be x raised to power 6 minus x raised to power 6 minus 1 all over x raised to power 2 minus 1. So we here now, because this is not linear, we cannot do synthetic division. We have to do long division. Okay, so we can then say, using long division. I mean, we use long division under polynomial division, and after then we've been using synthetic division because we've been dealing with linear divisors, right? So here now for long division, the thing is, you don't forget that this is x raised to power 6. Everything that is missing you have to put. So you have 0x raised to power 5 plus 0x raised to power 4 plus 0x raised to power 3 plus 0x raised to power 2 plus 0x, plus 0x before you now get to the minus 1. Very important to do that. Okay. So now we now divide by x squared minus 1. That's what we're dividing by. So every exponent in between must be taken care of. So first we start x squared into x raised to power 6. We have x raised to power 4. So x raised to power 4 times x raised to power 2. We have x raised to power 4 times x raised to power 2. That is x raised to power 6. Then of course there's every other thing. We have x raised to power 4 times x times minus 1. That is minus x raised to power 4. So we have minus x raised to power 4 here. And of course, we can just take care of this with maybe plus 0x raised to power 5, because that one too doesn't have it. So we can subtract here. Yeah. So we then have, this cancels out at this point. Then this also cancels out. So we then have 0 minus this. So we have x raised to power 4 right here. And then we can bring down 0x cubed plus 0x squared. Okay, man, let's just, yeah, we're going to have, yeah, so let's just leave this first, right? So we can just bring down the next one, at least for now. So x raised to power 4, so this x raised to power 2 now in x raised to power 4, that'll be another x raised to power 2. So x raised to power 2 times x raised to power 2, that's x raised to power 4. Then x raised to power 2 times minus 1, that is minus x squared. So we need to bring down this 0x squared too. So this one doesn't have 0. It doesn't have x cubed, so we just say 0x cubed. Then x squared minus x minus 1, that's minus x squared again. So now we subtract, this cancels out, and then we have 0x squared, 0x squared minus x squared, that's simply x squared here. And then we bring down 0x minus 1. Okay. So we bring down 0x minus 1. So next, we can then have x squared in x squared. That's plus 1, clearly. So 1 times x squared, that is x squared. Then 1 times minus 1, that's minus 1 here. And we have just 0x, since that doesn't exist. So we can subtract. So everything just goes, everything cancels out. So clearly, the other factor apart from x squared minus 1 will be x squared plus x raised to power 2 plus 1. Okay? So Um, so we can then rewrite, can say, therefore, therefore, x raised to power 6 minus 1 is equal to x squared minus 1 into x raised to power 4 plus x raised to power 2 plus 1. I think that's what we have, right? So now this one is settled. We don't have a problem with this. But this part now, we need to do another surgical operation on it. So we need to factorize that part. So we say to factorize x raised to power 4 plus x squared plus 1. Okay. What can we do here? Trying to see x raised to power 4 plus x raised to power 2 plus 1. So if we need to take care of this, we may have to do the whole perfect square thing that we did the other time with one of these expressions. So you see x raised to power 4 plus x squared plus 1. If you do uh, x squared plus 1 squared, okay, I think I need to do that by the side, right? X squared plus 1 all squared is like x raised to power 4 plus 2x squared plus 1. Okay, so I think we can come from this angle. So we have x raised to power 4 plus 2x squared plus 1. So how do we introduce this idea now? So we already have x squared plus 1 here. So we have x raised to power 4. Okay, okay, let me write with another marker. We have x raised to power 4 there. Then we have plus 1 also. So we need like x squared plus x squared minus x squared. I'm bringing in x squared plus x squared minus x squared because at the end of the day, I want to be able to get this out as 2x squared. And we already have plus 1 here. So that everything is balanced. I've not done anything wrong technically, right? So x squared cancels x squared. So we still have the same expression. So except that now I can then have x raised to power 4 plus 2x squared minus x squared plus 1. So you can see I have skillfully brought in minus x squared here so that now if I put this, and this together, I have a perfect square. So I have x raised to power 4 plus 2x squared plus 1 together minus x squared. So this is x raised to power 4 plus x squared plus 1 now. So this is now equal to, the whole thing is now x squared plus 1 all squared minus x squared. Okay? So now we have difference of two squares sweetly, and that will be uh difference of two squares, that's x squared plus 1 into, so x squared plus 1 minus x, all of that into x squared plus 1 plus x. Talking about difference of two squares, like x squared minus 1 is x plus 1, x minus 1. So now it's x squared plus 1 minus x into x squared plus 1 plus x. That's all this one is telling us. So we then have x squared plus 1 minus x into x squared plus 1 plus x. Okay, so that this is now, so x raised to power 4 plus x squared plus 1 is the same thing as x squared plus x, x squared minus x plus 1 into x squared plus x plus 1. Okay, carefully so. So x squared times x raised to power 4. We have x raised to power 4, right? Then x squared times x cubed. So I mean everything is basically in order like this. So now we have broken it down further into quadratic expressions. So don't forget where you're coming from. Don't forget where you are coming from. We already have x raised to power 6 minus 1 to be x raised to power 2 minus 1 into, so this expression now, x raised to power 4 into x squared plus 1. So that will now be x squared minus x plus 1 into x squared plus x plus 1. So we're expecting 6 roots. We already have 2 from here, right? We have 2 from here. We're going to get 2 from here. We're going to get 2 from here. So these ones are real, and these ones are most likely complex, right? So these ones are most likely complex, but let's see. Let's look at it. So for the first one, x squared minus x plus 1. Okay, so we have a equals 1, b is minus 1, c is 1, 2. So maybe I should even do it side by side. So for this now, we can get the root straight. X is equal to minus b, that's minus minus 1, plus or minus square root of b squared, that's minus 1 squared, minus 4 into 1, all over 2a, that is 2 times 1. So on that side, so we have x is equal to 1 plus or minus root 1 is this 1 minus 4 all over 2. Okay. Yeah, 1 minus 4 over 2 right there. So we have x is equal to 1 plus or minus root 3 minus plus or minus root minus 3 over 2. So x is equal to 1 plus or minus root minus 3 is I root 3 all over 2. So if we can split it up and say this is half plus or minus I root 3. So we have these two roots here. So on the other side too, we can go on and take care of that. So we can take care of this also. We have for x squared plus x plus 1. So a is 1, b is 1, c is 1. So x is equal to minus 1, plus or minus square root of 1 squared minus 4 into 1 all over 2 times 1, which is 2. So x now is equal to minus 1 plus or minus uh, root minus 3 over 2. So that is x equals minus 1 plus or minus I root 3 all over 2. So again, we have x to be minus 1 over 2 plus or minus I root 3. Okay, so we have another two solutions here. So with this, we have everything complete. So we have the 4 here and the 2. So we can go back to the beginning again and say, therefore, x raised to power 6 minus 1 is the same thing as x squared minus 1. Okay, x squared minus 1 into into uh okay, I mean, let me just write everything out at once so I don't waste my time again. So we have x raised to power 6 minus 1 into x minus 1, x plus 1. That's talking about the real parts. Then the other ones now. For the first one, we have x minus 1 over 2 plus I root 3 over 2. Okay, I mean, this should be over 2 now. So everything over 2, sorry. Yeah, everything over 2. Yeah. So x minus this, all right, into x minus 1 over 2 minus I root 3 over 2, okay, times, I mean, we still continue, x minus 1 over 2, that's this first one, minus 1 over 2, okay, plus I root 3 over 2, like that, into x minus 1 over 2 minus I root 3 over 2. So you see we have the 6 roots now. So we have the roots 1, 2, 3, 4, 5, 6. And that is what we have there. So it shows you that every kind of polynomial can be factorized totally, even if they don't have real roots. So with this, we come to the end of this interesting video talking about the fundamental theorem of algebra, which tells us in the basic form that for every non-constant polynomial with complex coefficients, there's at least one complex root. But in the strict sense, every polynomial of degree n with complex polynomials, every non-zero polynomial of degree n with complex coefficients rather has exactly n complex roots. Paying attention to the fact that real numbers, even when you have real roots, they are also subsets of complex roots. Thank you so much for listening, and let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Okay. Yeah. If you have subscribed already, I thank you very much. If you have not subscribed, what are you waiting for? You don't want to keep missing out on this kind of very important knowledge. So subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of the channel by hitting on join, click on join and become a special member of this channel. And that gives you some special privileges like hanging out with me if you're in the same geographical location at any point in time, or we can even hang out online to talk about anything that interests you on my channel, be it it mathematics, machine learning, data analysis, data science, whatever, scholarships, writing books, whatever interests you, we can talk about it. So ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.